statistically consistent phylogenetic inference using k-mer frequencies. And I have two collaborators, Elizabeth Ballman and Seth Sullivan. Okay, so the problem is that standard phylogenetic tree inference requires that you have aligned sequences. So you have to determine where you believe insertions and deletions are. But the alignment itself is usually found by assuming you have a tree, some sort of a guide tree found by some heuristic method that's not based on any evolutionary model. And so there's something that's sort of not model-based that's underlying all of this. And there's three possible things one might do. So the first two are already well known. You can try to both simultaneously align your sequences and infer the tree, but that's computationally very difficult, so it tends not to work for very many sequences at once. Another approach, which has been implemented in satay and pasta, is you align your sequences, you infer a tree, you take that tree to realign your sequences, infer a new tree, and repeat that a few times. Seems to work a bit better. And then the third alternative, which has not really been explored much, is a model-based approach to alignment tree inference. So most of the current alignment-free methods really don't use a model at all. It's just heuristic. Okay, so the framework that's going to be followed is we take our sequence, so there's a short one there, and I pick a value of k, like 3, 5, 7, somewhere in that ballpark, and I count the frequency of each k-mer. So for instance, for that sequence, ACG appears twice, so it's 2. CGT only appears once, so it gets a 1. And then I summarize my sequence by just this vector here of all of these numbers of the counts of the k-mers. And then I'm going to entirely base everything on working with that vector from now on. Okay. So the usual heuristic ways that you work with this is you take those vectors, one for each sequence, and then you somehow measure the difference between them and treat that as a proxy for distance along the tree. So you might just take the difference of the two vectors and their L2 norm of that. You might look at the angle between the two vectors, that's what that second one is there. Or you might do something a little bit more complicated, but whatever you do there, those are generally just things that people tried and they observed that they work well or don't work well. And then once you have those distances, you do some distance method, UPGMA, but everybody knows not to do that usually, neighbor joining or some other distance-based method to choose the tree. So this is the one theoretical result I'm going to give. I'm going to mostly give you simulations, but there's a proof of this, that the expected value of this L2 norm between these k-mer frequency vectors is given by this formula. Okay? And this is assuming a Jukes-Cantor model of sequence evolution with no indels, and I'll come back to that. And so the Jukes-Cantor model, really the only parameter I have is the distance along the tree. That's what t is, and I have this nice formula saying what that expected value should be. I will say there's a much more general version of this for up to the general Markov model. So basically any standard phylogenetic model without rate variation, we have a formula for. And what that means is that if you just simply invert this formula, you solve for t, you have a formula for the distance along the tree in terms of that L2, expected L2 norm of these k-mer frequency vectors. So you can recover the tree difference distance from looking at the k-mer frequency vectors in a consistent way. I'm not going to show this, but one implication is that it sort of shows that what everyone else is doing with k-mer frequencies is not a statistically consistent way to get the trees. You can play with this and see that that's what they're doing is going to, actually, as you get longer sequences, is more likely to infer incorrect trees. Okay, so, but if you want to use this to develop a method of consistent tree inference, okay, then you're going to define the distance between two taxa as this formula. And so I'm specializing to the Jukes-Cantor model just to keep the formulas a little bit cleaner. And so if I can just get this expected value of the right here, then I can recover the distance well, and then I can do standard tree building to get the phylogeny. So if I'm going to use this, I have to get this estimate, okay, of that expected value. Okay. So the naive thing to do, which doesn't work well, is if you want the expected value of that, well, you've got your sequences, you just compute the different, oops, let me get that. You compute the difference of these two vectors. take their L2 norm, and you use that one value as an estimate of the expected value. And that does work. It's much better than nothing, but it has a pretty high variance, and so it doesn't work that well. And a better way of approaching it, which is an idea that appeared in another paper of Sebastian Rock and a collaborator, is to take your sequences and break them into a bunch of blocks that are roughly orthologous. And for each one of those pairs of blocks, you compute this, and then you average across the blocks. This is a standard way of improving an estimate. Okay? And I do want to be clear here. The derivation that I've done or shown assumes no indels, okay, which sort of defeats the point of doing k-mer methods. If you have no indels, you've got a perfect alignment. But this appears to work quite well even with an indel process. Okay, so there's no proofs about that, but so the theoretical result is the first step. It needs to go further, but already it's going to show some nice improvement on things. Okay, that is not. There we go. Okay, so I'm going to talk about how this works well, or how well this works in simulation. And so just to remind you of a standard way of investigating this, I'm going to use the approach that Wilson-Beck used many years ago to compare a bunch of different methods. I'm going to focus on 4 taxon trees where I have 2 branch lengths, A and B. Okay? Actually, A and B are not branch lengths. They're the probability of a change along those edges at a particular site. And I'm going to produce a diagram like this, where this is the A-axis going from 0 to 0.75, the B-axis from 0 to 0.75. And what the plot shows is, for each value of A and B, I generate 100 collections of sequences, I infer a tree, and I record how often I get the correct tree. So if you see red there, that's 100% correct. So the dark red means the method is working really well. Dark blue is 0% correct, and this sort of turquoise is 1/3 correct. So that's basically random behavior. And this corner up here is the usual Felsenstein zone where you have long branch attraction. Okay, the baseline for comparisons, so these are all the baseline, is what I'll call the standard analysis, which is we produce an alignment, or we know the alignment already, either one of those, and we use Jukes-Cantor distance to correct, get a correct distance, and then we just use neighbor joining to build the tree. And so this diagram over here on the left, this is using the true alignment. Okay, so there's no error coming from the alignment, and you get very good performance on pretty much every tree, except for really extreme values where you have almost no phylogenetic signal left. This is the figure you get if you take rather long sequences. So these are 10,000 base pairs. They're generated by the Jukes-Cantor model with no indels. Okay, so in theory, if I just took those sequences and treated them as a line, I would have gotten this. But what I'm doing instead is running them through a standard alignment procedure. Okay, and this is just whatever was on the NCBI website with its default parameters. So I'm not saying I'm doing the best alignments, but what you see is there's this tremendously large area there where you're getting the wrong topology. Okay, so this is all error introduced by doing an alignment. Okay? Not a sophisticated one where I've thought about it hard, just using default parameters, but you see that much of that figure is really irrelevant if you are aligning your sequences. You know, in this region, there's enough changes that the alignment programs think we need to move things around and put in indels, and they're doing it, and then that's the result. Okay? And then this one over here, and this is rather surprising, here we do introduce indels. We're using the indelible program, so standard ones with a particular model of indels, and I'm not going to give the parameters right here. These are sort of more normal length sequences, but it actually performs a little bit better because, well, who knows why. Okay. Okay, so this is 2 slides showing the use of our formula. Okay, this is with particular choice is we're using 3-mers, so they're not even very long. 1,000 length sequences and with neighbor joining, and we have no indels, okay, in the data that was generated. And we are first treating this as one block, okay? So that means I get one number to estimate that expected value, and I don't do a very good job. But if I take that sequence and chop it up into 5 blocks, each of length 200, I can do better. 25 blocks of length 40, I do better. 100 blocks of length 10, 250 blocks of length 4. And this particular one, if I make more and more blocks, I continue to do better because there are no indels, and so each of these blocks is really perfectly aligned. Okay? So that's no big surprise, but that's also not indicative of what you would see in the real world. Okay. This one, I have some indels, and these are the particular parameters that Indelible uses about how often indels come in and their length distribution. And I do something similar, and here you see that the performance improves for a while and then starts to degrade. It degrades here because my blocks are becoming so small that with the indel process, there's a good chance that 2 blocks don't actually have anything orthologous in them. There are no orthologous sites. They've been shifted over by the indels. Okay, but so there's some sort of mid-size where things work better. And by the way, so this is with indel data. Again, the formulas behind this were not derived making an assumption of any indels. Okay, so to compare this to the traditional method, this is just one particular comparison. You can ask, is the k-mer method better than doing pairwise alignment or not? Okay, so this particular simulation using 1,000 length sequences with certain indel process, I'm choosing to use 5mers with 25 blocks in neighbor joining. This is the figure you get with the standard alignment method. Okay, so I am generating sequences with indels, I'm aligning them, and then I'm using the alignment with the Jukes-Cantor distance to the perfect tree. Okay? And you see rather pronounced long branch attraction up in that corner, okay, stretching down quite a ways. This is the same data with the k-mer method, okay? So no alignment is ever produced. And that red region is actually larger than it was in producing the k-mer. Even up here, well, you know, this is being about 1/3 correct. That may or may not be anything too excited to get about, because really, I mean, I think phylogenetic inference is going to be more down in the lower left-hand corner. And what matters the most, I think, is that this long branch attraction problem has sort of gone away. Okay? And for comparison, this is the scale here is a little hard to interpret. It's not the same as these. This figure is that one minus that one. Okay? And so where you see red, that's where you're getting the biggest improvement. Yellow, you're getting an improvement. Even the turquoise, you're getting an improvement. Blue, you're not getting an improvement. And so it's significantly better over a bigger region. And I'm not showing it in the talk, it's in the paper. We did this for a bunch of non-model-based k-mer methods, the thing that typically underlie finding guide trees to do alignments, and they generally perform worse than this. Okay, so, all right. There's a lot more to be done. The point is, these methods can be statistically consistent if you work hard enough, take a model into account in trying to derive the formulas. Even if you have an indel process, as long as your blocks are approximately orthologous, it still appears to work well. We'd like to have theoretical results for that, but we don't yet. There's a lot more questions that remain. We're not investigating this with large trees, which is what lots of people do, but we wanted to stick with small ones where we could understand what was going on. We definitely need to extend this to an indel model, and the question is, would this be, even if you want to use an alignment, could this lead to more effective guide trees than what's being done now? 2 references, our paper to appear is already on the archive, and one that should get some credit by Sebastian Rock and his collaborator, does not look at k-mers at all, but it set us up to be thinking